Next, we have two connected talks separated by the coffee break. And the first of these is given by Apala Majumdar from Bath University. So over to you.
So firstly, I'd like to thank the organizers for the invitation to speak here. And as you can tell from the title, I'm going to talk about some of our recent work. So that's me and my collaborators' recent work on the mathematical and numerical modeling of a planar two-dimensional liquid crystal device. Now, before I start, I wanted to speak very briefly about my research themes, my research program. So most of my work to date has focused on continuum macroscopic theories for nematic liquid crystals, mainly mathematical analysis of the Oseen-Frank and the Landau-Dijen theory for nematic liquid crystals, especially in the context of defects. And I've also worked at the application of these theories to the modeling of liquid crystal devices which are manufactured by industry, for example, by Hewlett-Packard. And more recently, I've become interested in the relationships between microscopic models and macroscopic theories for liquid crystals, particularly in relation to multi-scale theories for nematic liquid crystals. And a part of this talk today, it does focus on the relationship between lattice-based intermolecular interaction potentials for liquid crystals and the full macroscopic Landau-Dijen theory for nematic liquid crystals. But this will hopefully become clear as the talk progresses. So almost all of my research to date has focused on nematic liquid crystals. That's pretty much all I've done. And as most of you will know, that nematic liquid crystals have widespread applications in science, technology, and even biology. And notably, they pretty much form the backbone of the liquid crystal display LCD industry, which is a pretty large industry. So the question then is, what makes nematic liquid crystals so useful for optical applications or display applications? And the key word here is anisotropy. Basically, these nematic liquid crystals, they have preferred directions of molecular alignment. So they have directional physical properties. They have different physical properties in different directions. So namely, they are optically anisotropic, birefringent. So they respond differently to light traveling in different directions. They're very sensitive to external electric or magnetic fields. They're also very sensitive to boundary effects. So what I'm really trying to say here is that it's fairly easy to manipulate a nematic phase or the molecular alignment by external effects. Now, since this talk is really about the modeling of liquid crystal displays, I just want to spend a couple of slides very briefly describing the working principle of an LCD. And nematics have two key properties which make them very useful for display applications, like I've already said. They're optically anisotropic and they're very sensitive to external electric or magnetic fields. And here I have a picture of the very commonly used twisted nematic display. And as you can see from the picture, the basic construction is fairly straightforward. It effectively just has a layer of liquid crystal material sandwiched between two solid surfaces. And both of these surfaces, they are treated so as to induce a preferred liquid crystal orientation. So in some sense, the orientation is fixed on these two surfaces. So mathematically, it's a Dirichlet boundary value problem. And the key point is that in the absence of an electric field, the molecules, they twist uniformly between these two plates. And the twisted structure, which is the picture on the left, is transparent to incident light, so it allows light to pass through. But then when we apply an electric field, the molecules, they tend to line up with the electric field. And the aligned structure, which is the picture on the right, is opaque to incident light. But the problem is, once you remove the electric field, the molecules will spontaneously relax back into the twisted, transparent state. So in this sense, it's a monostable device because only one of the states is stable without an external electric field. So this brings me on to bistable displays, which is pretty much the focus of today's talk. And the working principle of a bistable display is easy to understand. It's basically a geometry which can support multiple optically contrasting states in the absence of an electric field. So both the bright, the transparent, and the opaque states, they are stable without an external electric field. So you only need power to switch between the contrasting states, but not to maintain them individually. And clearly, if this construction is successful, then this is very useful for devices which maintain a static image for a very long period of time, because you don't need, in principle, you don't really need power to maintain an image. You only need power to refresh the screen. And most of the work that I do in this area is motivated by the mathematical and the numerical modeling of bistable LCDs. So the question then is, how can mathematical modeling help help in this in bistable display design? And the first point to make here is that bistable displays, they typically use a combination of a complex geometry, a micro-pattern geometry and complex boundary conditions to stabilize multiple optical contrasting states. And for example, a key question from industrial researchers is often, what is the best way to use the geometry and the boundary conditions to induce bistability or multistability? What is the role of the geometry and the boundary conditions? Secondly, can we use mathematical modeling to actually predict the structure and the alignment of these alignment structures of these static physically observable equilibria in these bistable geometries? Very importantly, what can we say about the switching mechanisms? How do we switch between the different optically contrasting states? How can we optimize switching with respect to the geometrical and the material parameters? And last but not the least, what can we say about optical properties? But this is really in the realm of inverse problems, and I don't really work in that area, although I think there's some recent work in Oxford on inverse problems, but I don't really work on inverse problems. So most of my work is really on the continuum analysis. So here I have some pictures of bistable displays. So these two pictures, they are pictures of two-dimensional or planar bistable liquid crystal displays or devices. Now they're planar or two-dimensional really from a modeling point of view, in the sense that we have used a two-dimensional model to model these devices. But it's quite possible that you can get new phenomena by adding a third dimension, but we simply just haven't done that yet. But the next one, the post-aligned bistable pneumatic device, which was designed by Hewlett-Packard Laboratories, is a truly three-dimensional device. So this was part of my graduate work with Jonathan Robbins, Maxim Ziskin, and Chris Newton. And this was a question posed to us by Hewlett-Packard. But one of the main outcomes of our work was really a new topological mechanism for bistability in the PABN geometry. So what our mathematical modeling told us is that this geometry or device is bistable or multistable because it can support multiple topologically distinct stable equilibria. So it's bistable because it can support topologically distinct local energy minimizers. And because these states are topologically distinct, they're naturally separated by an energy barrier, which in turn leads to their long-term stabilities in the absence of an electric field. Now for the rest of the talk, I'm going to talk about a two-dimensional planar bistable liquid crystal device. And this was first reported in a paper by Sakonas, Davidson, Brown, and Mottram. So this is really what motivated our work. Now this work, my work, is joint work with Chong Liu and Radek Urban. And a large part of our work is really carrying out a detailed numerical investigation of this 2D bistable device within the continuum Landau-Dijen framework. But we've also followed it up by some simulations with using lattice-based and off-lattice intermolecular interaction potentials for liquid crystals. Now just to give you some background, here I have a picture of this 2D bistable device. So as you can see from the picture, the basic construction is easy to understand. It's basically just a periodic array of square or rectangular liquid crystal wells filled with liquid crystal material. These wells are fairly shallow. This just means that the height of the well is pretty small compared to the cross-sectional parameters. From a modeling point of view, we are really only going to look at what happens on the bottom cross-section of the well. In this sense, this is two-dimensional. So we're going to neglect any variations across the height of the cell. So we're going to treat this to be a two-dimensional modeling problem. So our computational domain is just a square or a rectangle, so that makes it easier. And in terms of boundary conditions, these wells or surfaces, they are treated so as to induce planar or tangent boundary conditions, and I'll tell you more in the next slide. So from a modeling perspective, we are effectively just looking at a square or a rectangle. We're working in a completely 2D framework, and the tangent boundary conditions really just mean that the liquid crystal molecules, they have to be in the plane of the square. So these are 2D configurations on a 2D domain. Now you have tangent boundary conditions, so this means that on the edges, the molecules have to be aligned along the edges. So on the horizontal or the x edges, the molecules just have to be horizontal. On the vertical or the y edges, the molecules have to be in the y direction, they have to be vertical. But as you can see from the picture, this will naturally induce some misalignment at the corners, because the two alignments, they can't match at the corners. So you will necessarily have some sort of defects at the four corners. And this is all that I want to say on this slide. Now, like I've already said, this device was first reported in this paper by Sakonas, Davidson, Brown and Mottram, and experimentally it was found to be bistable. So they found at least two stable states. And the first state they found, it was labeled to be the diagonal state. So as you can see from the picture, in a diagonal state, the molecules are roughly aligning along one of the square diagonals, and you clearly have two possibilities because there are two diagonals. And the molecular alignment is really just, it has a radial flow pattern between these two defects, which are at diagonally opposite vertices. So the only thing about the structure that we need to take away from this slide is that the alignment is roughly, it is diagonal, it's along one of the square diagonals, and you have these two defects, real defects, which cannot be eliminated by smoothing the corners. You have these two radial defects at diagonally opposite vertices, and there are obviously two choices for the square diagonal. Now the second state that was reported is what they call the rotated state, and here the alignment flips by pi, or it rotates, it does a half turn as you move between a pair of opposite edges. And there are clearly four equivalent rotated states, which are just rotated by a rotation of 90 degrees. So you would have two states which are more horizontal in the interior and two which are more vertical in the interior. But the main distinction here is that the two defects, the two sort of real defects, they are now along two vertices which are connected by an edge. And both the diagonal and the rotated states, they have long-term stabilities. So was reported in the paper. And in this sense, this simple geometry is bistable. And here I have some pictures which are again taken from their paper, where they were looking at the optical properties of these two states. So our goal was, and still is, because there's still more work to be done, is to develop a complete mathematical model for this device, which can account for the boundary conditions, the strength of the surface anchoring, and which can also account for the switching mechanisms. So how do you switch from the diagonal to the rotated state in the presence of an electric field, and vice versa. So we've done all our macroscopic modeling, the continuum modeling, within the Landau-Dichen theory for nematic liquid crystals. And the Landau-Dichen theory, as most of you will know, is a very successful continuum macroscopic theory for nematic liquid crystals. But it is really macroscopic in the sense that it has no microscale information. It has no information about either the molecular shape or the nature of the intermolecular interactions. And this is related to the second part of the talk. But it describes the state of the nematic liquid crystal by a macroscopic state variable, which is the Landau-Dichen Q-tensor order parameter. The Landau-Dichen Q-tensor order parameter is really just a macroscopic measure of the anisotropy present in the system. But from our point of view, since we're really just looking at two-dimensional configurations on a strictly 2D domain, the Q-tensor order parameter is just a symmetric, traceless 2x2 matrix with two independent components, Q11 and Q12. So we're effectively just wanting to look at these two components. But we want to relate this Q-tensor to the degree of orientational ordering and the direction of preferred alignment. So we're also going to use this alternative representation, and the S that you see in the formula is the scalar order parameter. So this is related to the degree of orientational ordering present in the system, and the N is the distinguished direction. It's a measure. It represents the preferred direction of molecular alignment. And because this is a strictly planar 2D framework, this N is fully characterized by this angle theta. It's fairly simple. And because we're really only working in two dimensions, we have a very neat analytic prescription for the defect set. The defect set you can rigorously show is just the isotropic set of the Q-tensor order parameter. It's just a zero set of the scalar order parameter. And it's worth pointing out that you don't really have such simple characterizations in 3 dimensions. So if we were working in 3 dimensions, it's not complete. Your defect characterization would necessarily be more complicated. But here, computationally, we are really just looking for the zero set of the scalar order parameter, and that makes life easier. So the Landau-Dichen theory is a variational theory, and we want to look at the stable equilibria. So effectively, we're just looking at local or global minimizers of a suitably defined energy functional. So we've looked at strong and weak anchoring separately. So strong anchoring is just it's effectively when the Q tensor is explicitly prescribed on the boundary, in our case on the edges of the square. So it's just a Dirichlet boundary value problem. And in this case, our Landau-Dijon energy, we're really working with something which is very simple. The elastic energy is just the one constant elastic energy, grad Q squared, sum of the squares of the first derivatives of the Q tensor. The second term that you see there is the bulk energy. It's just the thermotropic energy. It dictates the degree of orientational order, or the bulk ordering. Now the epsilon that you see here, it's like a penalty term, so it's familiar to people who work on Ginzburg-Landau theory. I should say that everything has been rescaled here. This is all dimensionless, and I'll talk about the rescalings in a minute. But the epsilon is really just a penalty term, and it's really related to a characteristic defect size, the nematic correlation length. It depends on temperature, but a lot of our simulations are for fixed temperatures and a low temperature well below the nematic isotropic transition temperature. So epsilon is typically very small in our simulations, and in the Dirichlet case or the strong anchoring case, we're really just computing local minimizers of this fairly straightforward Landau-Dijon energy functional with just these two separate contributions. But the problem is, or so I believe, is that Dirichlet boundary conditions are not really very physically realistic, because it's hard to prescribe a boundary condition exactly. So it's probably more physically realistic to introduce a surface anchoring energy which somehow enforces the tangent boundary conditions. And this is what we've done in the weak anchoring case. We've introduced a surface, well, it's not really, it's Durand and Nobili surface anchoring energy, but we've introduced this Durand-Nobili surface anchoring energy. The W that you see here is a rescaled anchoring coefficient. So larger the W, the more strongly the tangent boundary conditions are enforced. And you also see a G1 and a G2 here. This represents the idealized orientation on the boundary or the preferred orientation. So you could ask me, where do we get this preferred orientation from? And I will answer that question. We have this procedure for computing our preferred orientation. But for the time being, it's the preferred orientation on the boundary. And then I have some comments on the rescaling, because everything here is dimensionless. So the epsilon, I'm sure it's familiar to people who work on liquid crystals. It depends on the elastic constant K, the domain size D, and it also depends on the temperature. The W, which is the rescaled anchoring coefficient, it depends on the real anchoring coefficient, which I've called WANC here, WANC, the square domain size D, and the elastic constant K. But I think these rescalings are pretty much standard in the literature. It's not fair, it's not new. And of course, we also want to look at switching between the different states in the presence of an electric field. In this case, we have just added an external term, which accounts for the interaction between the electric field and the Q tensor order parameter. And then a lot of this, at least a fair part of this work, is really just about then numerically solving the resulting Euler-Lagrange equations or the evolution equations in all three cases. And then we have the microscopic work as well. Now for the strong anchoring, let's just first start by thinking about what sort of boundary conditions are actually admissible. What conditions do we need on this vector G? And then we can talk about the optimal G later. Now, if you recall, we have tangent boundary conditions. Now, this necessarily means that there is some misalignment at the vertices. So there are defects at the corners. So any admissible G has to vanish at the corners. So when you construct an admissible G, it has to vanish at the corners. But we're also working with low temperatures, so epsilon is typically very small. And this means that your mod Q, it wants to be almost 1 almost everywhere except for the defects. So you really want your G to be almost 1 pretty much everywhere on the square edges except for at the vertices where G has to vanish because we have defects. And for every such admissible G, and this is again I think standard, you can write down the Euler-Lagrange equations in weak form and solve using finite element methods. And if you do that, for every admissible G, we will find 6 different solutions depending on the initialization or the initial condition. So here we have found 2 diagonal and 4 rotated solutions for every admissible G. Here I have a picture of a typical diagonal solution, a typical rotated one, and all 6 on the same slide. But this is to be expected. For every admissible G, we do get the 6 different solutions that were reported in this paper by Sakonas, Davidson, Brown, and Mottram. But then the question is, you clearly have an infinite number of possibilities of G. You can construct a complete a continuum of functions of vector fields G which satisfy these minimal conditions. So how do you choose the best one? What's the definition of an optimal boundary condition, or what's our definition of an optimal boundary condition? At this point, we've introduced a second variational problem. This is not a Dirichlet boundary value problem. It's a second variational problem, and the constraints are minimal, consistent with the tangent boundary condition. So if you look at these formulae, you will see that the functional spaces are different. So I'm not giving too much background at this stage, but the point is, this is a different problem. It's not a Dirichlet boundary value problem. It's a constrained variational problem. You're still solving for these two independent components, Q11 and Q12. There is a constraint. The constraint is now just that Q12 has to vanish on all 4 square edges. And without giving you further detail, this is a minimal constraint that is consistent with the tangent boundary conditions. Just the fact, it's not a Dirichlet boundary value problem. We just want Q12 to vanish on all 4 square on all 4 edges. But the point is, again, depending on the initialization, for every fixed epsilon, we do get 6 different solutions. We get 2 diagonal solutions and 4 rotated solutions. But we call these solutions optimal solutions. This is just our definition or our labeling. We call these solutions optimal solutions. And to understand why we call these optimal, let's just look at the diagonal solution to start with. Like I've said, if you fix your epsilon, for every G, we are going to get a diagonal solution. So there is a whole continuum of diagonal solutions. And the optimal solution, the optimal diagonal solution, is the one which has the minimum energy in the space of all diagonal solutions for a fixed epsilon. So in this sense, we call it optimal, because you have this whole continuum. For every G, you have a diagonal solution. And the solution of this variational problem, because this has the minimal constraints consistent with the tangent boundary conditions, we say it's optimal because this has the minimum energy as found from the numerical simulations in the space of all diagonal solutions. And we have 6 different optimal solutions, 2 optimal diagonal ones and 4 optimal rotated ones. And then you can just extract their boundary values. You define their traces to be the optimal boundary conditions. So for every fixed epsilon positive, we have 6 optimal boundary conditions, or what we call optimal boundary conditions. And this, I think, is a nice concept, although this may need to be further refined, because in some sense, this does prescribe the optimal interpolation between the 4 defects at the 4 edges. And here I have some typical solution profiles. This is the optimal diagonal and the optimal rotated solution. And as you can see, you do have the 4 defects at the corners, which is exactly what you would expect for a strong anchoring problem. So next I have the weak anchoring problem. So here we don't really have Dirichlet conditions anymore. Instead, the tangent boundary conditions are enforced by imposing a surface anchoring energy in terms of a surface anchoring coefficient W. And we are really looking for 3 key properties. So we want this problem to have solutions for all values of W. We want the weak anchoring solutions to converge to the strong anchoring solutions as W becomes very large. And we want the scalar order parameters to be bounded for all W and epsilon. And this was one of the, so there are multiple choices of the surface anchoring energy in the literature, but it turned out that the Durant-Nobili and this particular form of the surface anchoring energy was best suited for all these 3 criteria, and therefore this is the one we used. And the rest, again, we just write down the Euler-Lagrange equations in weak form, and we solve using finite element methods in the weak anchoring case. So we have looked at the multiplicity of these solutions as a function of the anchoring coefficient. And the main point here is that we again recover multistability. We get the 2 diagonal solutions and the 4 rotated solutions, provided the anchoring coefficient is sufficiently large. And we can give quantitative estimates for this critical anchoring coefficient. But what is probably more interesting is rather defects or the lack of them when we go from the strong anchoring to the weak anchoring case. Because here I have the profiles. It's possible the pictures are not very visible, but the thing here is that the weak solutions, they don't really have any real defects or isotropic points. You do have regions of reduced order at the corners, but you don't have any real defects. And qualitatively, you can understand this because there's a competition between the anchoring energy and there's a competition between the bulk, the thermotropic energy, which has this small parameter epsilon. So we are working with low temperatures, so epsilon is small, so defects are energetically expensive. So if the anchoring is comparatively weak compared to this epsilon, or the magnitude of this thermotropic penalty term, then it's energetically preferable to break the anchoring near the vertices at the expense of avoiding these defects at the four corners. So it's just an energetic balance argument, and we lose these defects in the weak anchoring setup. So everything that I've said so far, both the strong and the weak anchoring, is really only for the static properties of this planar device. It's really only about the static equilibrium. But like I said at the start, we're also interested in modeling the switching mechanisms. We want a simple dynamic model for the evolution. And the model that I have here is really the simplest possible. It has the minimal physics in it. It's just a gradient flow model for the Landau-Dijon energy. Obviously, it can be much improved if we include fluid flow effects or backflow effects, but as a starting point, it does serve the purpose. So it has minimal physics. It's effectively just solving a system of parabolic PDEs. You have an extra term on the right-hand side, which accounts for the interaction of the electric field with the orientational order, or the coupling of the electric field with the Q-tensor order parameter field. And the important point, what was interesting, is we could only achieve switching by making the anchoring strength W different on the four square edges. And this was actually suggested by Nigel Mottram. So here I have a picture. And what we did is we made, here we're trying to simulate the switching between a diagonal state and a rotated state. If you look at the two pictures, they have different alignment on the top vertical edge, on the top edge. And what we did is we made W 10 times smaller on the top edge compared to the other three. And what happened then is, when we started off with the diagonal state as the initial condition, we applied an electric field along one of the diagonals. It's a material with positive anisotropy. Positive anisotropy means that in the bulk, at least, the molecules want to line up with the electric field. So in the bulk, the molecules wanted to line up with the electric field. But on the top edge, there was a competition between the anchoring energy and the electric field. And because the anchoring was comparatively weak, it was easy for the molecules, for the director profile, to break the anchoring on the top edge and be more aligned with the electric field. And then when we removed the electric field, the state naturally relaxed into a nearby equilibrium. But this nearby equilibrium was no longer the initial diagonal solution. Rather, it was one of the rotated states. And in this sense, we did achieve switching from the diagonal and the rotated, and we can also achieve switching in the other direction. You just make the anchoring weaker on the edge, which mediates the switching. And then the electric field will dominate the anchoring, and this will initiate the switching process. And I'm not quite sure how easy it is to realize in practice, making the anchoring weaker on one part of the domain, on one part of the boundary compared to the others. But mathematically, it was fairly straightforward to achieve switching. So all of this is really in a very continuum PDE-based framework. But like I've said, these PDE models, they don't really have any information about either the molecular shape or the nature of the intermolecular interactions. And to some extent, we do want to compare different liquid crystal theories on different scales and also different computational approaches. So this brings me to the second part of my talk, which is really about lattice-based models for liquid crystals. So I'm not an expert. Most of my work is on the continuum side of things. But I have a very straightforward picture here, and there are some experts in the audience on the more microscopic descriptions. But from our point of view, we have our square domain. We have a regular lattice on the square domain. At every site, we have a molecule, or more likely a cluster of molecules, and every site has an associated orientation, theta I, and every site only interacts with its nearest neighbors, the four nearest neighbors, and you have an interaction energy between the different sites, which is proportional to the relative orientations at the two different sites, and the total lattice energy is the sum of the interaction energies between the different lattice sites, obviously summed over all the lattice sites. and we want to minimize this energy, or we want to find local minimizers of this lattice energy using fairly standard routine Monte Carlo methods. We have with the Metropolis-Hastings algorithm. And because temperature plays a key role in our analysis, the temperature dependence is implicit in the Metropolis-Hastings algorithm. So we've pretty much applied this strategy to the Landau-Dijon model. So we have our square domain, we have a regular lattice. At every site we have this two-dimensional vector Q11, Q12. This is really just the Landau-Dijon vector, but defined at every lattice site. Every site only interacts with its 4 nearest neighbors, and then we've written down a simple lattice-based intermolecular interaction potential. Now, some of you will probably be wondering that this is really just a discretized version of the Landau-Dijon energy. We've just really replaced derivatives by finite differences. And the h that you see here is the mesh size, which in principle could be a microscopic parameter. But as it stands, it really doesn't look much more than a discretization of the Landau-Dijon energy. And the question then is, what do we hope to achieve by discretizing the Landau-Dijon energy? Because that's pretty much what you would do in a finite, in a PDE sort of setup. Well, the first point to make here that as it stands, maybe not much, but this is in principle a lattice-based intermolecular discrete interaction potential. So you can introduce more parameters into it. You can make it more microscopic in nature as compared to a traditional PDE approach. You can explicitly introduce dependence on molecular shape and nature of interactions. The second point is that even though as it stands is just a discretized version of the Landau-Dijon energy in some sense, you are solving it by completely different numerical methods. In the Landau-Dijon case, you're just using finite difference or finite element methods in the PDE framework. Here we're using stochastic numerical methods, Monte Carlo methods, and molecular dynamics. And in principle, this approach or this sort of parallel study could be useful for multi-scale liquid crystal theories, where we want to couple microscopic and macroscopic liquid crystal models. So we've done some analysis. So even with this lattice-based discrete intermolecular potential, we looked at strong anchoring, and we have been able to get the 6 different states. We just fixed the Q tensor on the boundary and let the interior state evolve, reach equilibrium. We've also looked at weak anchoring, and again we get multistability for reasonably large values of W. What is interesting, at least we thought, was we can also get switching, although it's not quite switching in the same sense. So we start with one of the states, say either the diagonal or the rotated. Now the key, we still make W different on the 4 different edges, so we still have the same concept of variable anchoring strength. But the main difference here is that now we don't really have dynamic equations anymore. So it's really more of a quasi-static evolution. So you start with a diagonal state, then you apply an electric field, use Monte Carlo methods to compute the new equilibrium in the presence of an electric field. You view this as a transient or an intermediate state, then you remove the electric field, and then with this new equilibrium as the new initial condition, and then you let it relax. You use Monte Carlo methods to find the final equilibrium again, and the final equilibrium again, the final state is now a different one. So if you start with diagonal, you end up with the rotated, or if you start with the rotated, you end up with the diagonal. But this is really a quasi-static evolution because we don't really have dynamic equations. We're just using Monte Carlo methods to compute different equilibria. Now, lattice-based models are kind of restrictive in the sense that they constrain the molecules to particular lattice sites. They have no translational freedom. So off-lattice models are often, they are considered to be more detailed. They have more information in them because they allow the molecules to have orientational and translational degrees of freedom. The molecules can move around. And again, there are some experts in the audience. So the Gay-Byrne model, we believe, is a very popular choice of an off-lattice intermolecular interaction potential. And we have tried to model this 2-dimensional planar device within the Gay-Byrne model too, but we have had, unfortunately, very limited success. So I don't really have time for details, but the Gay-Byrne interaction energy between a pair of molecules, it not only depends on the relative orientation of the 2 molecules, but also depends on the relative position of the centers of mass. Now, the Gay-Byrne the Gay-Byrne model, by definition, has more tunable parameters. In particular, you can even adapt it to a particular molecular shape. It has parameters which depend on the molecular shape as well. So it gives you a lot more freedom. But in our case, we found that the convergence in our case was very slow to the two different states. The convergence rate was very slow. And more often than not, we did not really get the two different states. We would often get stuck into some sort of a regime where we would get patchy monodomains. And we did actually get the diagonal and the rotated states, but only for some very special cases where we were effectively neglecting the attractive part of the Gay-Born potential when the attractive part was very weak. So we only got bistability for some very special choices of the parameters when the attractive part was very weak, and the convergence rate was really very slow. So we didn't really have a lot of success. And this was further confirmed by our work with the HGO model, which is really another form of the intermolecular interaction potential. So it has no attractive part. So for us, it was a variant of the Gay-Born model with no attractive part. It's just purely repulsive as far as we could. And the molecules, they can't really come too close together. They can't overlap. And we had the same issues. The convergence rate was very slow. But we did actually get both the diagonal and the rotated states after a very long time. But this is still work in progress. And the work is by no means finished. So I think I probably still have 5 more minutes. So I just want to very quickly talk about some very recent work on another bistable device, which is the zenithally bistable nematic device. So this is joint work with Peter Howell and Alexander Reich at Oxford. So I'll be very quick here. But the ZBND device, the geometry, it's effectively just a layer of liquid crystal material, again sandwiched between two surfaces. The top surface is flat and planar. On the bottom, we have some sort of a sinusoidal grating. Both of these surfaces, they are treated to have homeotropic or normal boundary conditions. And this device has also been reported to be bistable in the literature. It's even commercially available. And the two competing states are typically believed to be the vertically aligned state, where the molecules are pretty much vertical everywhere in the geometry, and the second state, which is called the hybrid aligned state. And this is sort of more horizontal near the grating, and you have these two defects which are pinned at the crest and at the bottom of the sinusoidal grating. So we had the same principle. We just wanted to model this device within the Landau-Diechene framework and find the static equilibria. And as you might expect, we did find the Van and the Han state, which are reported in the literature. But what was interesting is we found a third state. And I haven't seen this in the literature, but it's possible that I just haven't looked in the right place. We found a third state, which we call the hybrid Han state. And this is pretty much like the vertical Han state. It's pretty much vertical, but it's not defect-free. It has two defects stacked on top of one another. So it's possible that optically it is indistinguishable from the Van state because it is pretty much vertical, and these two defects which are stacked on top of one another don't really make much of a difference to the optics, and hence it hasn't really been reported in the literature. But we found this third state, and it is actually stable for a large range of our parameter values. And for the ZBND, the parameters are epsilon, which is pretty much temperature, the depth of your grating, and the depth of the cell, and it is stable for a large range. So we thought that was interesting. And the other thing we found, which we were pleasantly surprised by, is we could actually switch between the hybrid Han state, which is with the two defects stacked on top of one another, and the Han state, which has these two defects separated, just by varying temperature. So this is a switch. This sort of switching, there was no electric field. We're just effectively changing temperature to jump between the different branches of the stable equilibria, and this seemed to work in both directions. But because this is fairly preliminary work, it's probably best to check things again. But this was switching just by changing temperature, and that we thought that was nice. Okay, thank you for your attention.
Very much for a very nice talk. We have plenty of time for questions.
So for the square bistable device, is there any possibility for like a simple approximate solution by making up some variational form for what the director field might be, with just a few parameters and doing some paper and pencil minimization over those parameters?
Yes, so that's so we're doing that with the graduate student at the moment. We've been using the Osane Frank, which is even simpler than the Landau Dijon, which is effectively just the angle theta. And if you sort of take away small regions around the defects, you just solve the Laplace's equation on a 2D domain, which you can do by separation of variables. And you can get analytic estimates for the energies of the diagonal and the rotated states. And they're pretty good, actually. So you can do that. So, and you could probably use those as good initial conditions for your more sophisticated theories.
Can you get any kind of dynamics that way?
We haven't, yes, you can. I think the answer is yes, but we just haven't done that yet. But for the static solutions, yes, we can construct explicit solutions of the Laplace's equation. These are explicit formulae, and we have explicit energy estimates as well.
Question at the back.
Actually, I have two questions. What about the energies of the two rotated and diagonal states compared to the height of the energy barrier? And second, what is the difference in the optical properties of these two states?
The difference in the optical properties, I don't know much about. So the only optics I have are pictures that were taken from what the Sakonas's paper. So that I'm not. The only information I have about the optics is this. So there is some difference.
There is.
And about the energy estimates, it is similar to the first response, that yes, we can compute analytic, so at least in the Osane Frank framework, for the two stable states, the diagonal and the rotated, we can compute analytic expressions for the energy as a function of epsilon and also as a function of the aspect ratio, for aspect ratio of the domain. So these are analytic estimates for the energy. And how they relate to the energy barrier, well, I think we would have to do the dynamics more carefully, because the switching that we did was it was just to illustrate that we can just achieve switching by using this concept of variable anchoring strength. So I think that requires more work.
But, I mean, if we want to use this in a real device, we have to be sure that by thermal fluctuation we can move from one state to the other and fall in the minimal global minimizer of the.
The numerics indicate that that's probably quite robust. I haven't done the mathematics. We just have the estimates for the two states. But the numerics indicate it's robust.
Some more questions. Ben and then.
Okay.
Mike.
Me? Okay.
Yeah.
Sorry, I think I missed slightly in your simulation of the square device is two-dimensional. Obviously, the device itself is three-dimensional. I don't quite understand what the three-dimensional geometry actually is.
A box.
Yes.
So your 3D geometry would be some sort of a cube or an elongated box.
Is it thin in the third direction?
Yes, it is. That was
and is the idea that on the top and bottom plate there's negligible anchoring?
So it's tangent boundary conditions on the top and the bottom surface. So
but with free rotation?
Yes. So
okay.
The idea is that the profile is just repeating.
Okay.
So you model the bottom surface, and it's just repeating across the height of the cell.
Okay. And then for the final part on the ZBD device, that's slightly different, right? Can you remind me of the three-dimensional geometry of that?
So the modeling that we've done is strictly 2D. It's just a surface with flat and this grating at the bottom. The 3D geometry, I think the assumption would still be the same, that it's effectively it's just repeated across a very thin sort of a height. And in some sense, the modelers are arguing, or we think that it's enough to look at what's happening here, and it's just repeating itself. But it's quite possible that if you do a fully 3D, sort of a fully three-dimensional simulation, you get new effects. In particular, you get biaxiality, you get new phenomena.
Okay, thanks.
There was one at the back.
You've got this still on here. You've used this Q tensor in basically two-dimensional space for the orientation. So I think what people have done in the past is they fixed one eigenvector of the Q tensor to deal with two-dimensional orientation, which allows you to have biaxiality in your device. Now, you've got only two parameters left. Can you comment on what type of restrictions you expect to get from this?
What sort of restrictions? Well, I mean, it is restrictive because, there is no we haven't really accounted for it doesn't really give any insight. So now I think we're working with Samo Kraj from Slovenia, and we are accounting for the third dimension as well. So I think the main restriction here is that there is no proper accounting for biaxiality. I mean, the structure of the defects is not properly resolved. we can track the defects, we can locate them, but they're just located as mere zeros of the order parameter. It's not a good resolution of what's actually happening near the corners. But you could argue that maybe what's happening near the corners is not really affecting the macroscopic properties too much.
Did I miss a question here? Or?
Yeah, did you try to calculate the strength of the electric field you need in order to take the other state, to start from, let's say, the diagonal and to go to the rotated state in this discretized version of your theory?
Yes, we did, but everything is rescaled and it worked out to be 10 volts, but this is just one example.
Do you have critical values for this?
No, we didn't do enough, so it's no, because the dynamics was just to have a few examples where we can demonstrate switching. To have the critical strength, we would have to explore the parameter space systematically. In our case, we picked a few examples and it worked, and the electric field strength was about 10 volts for those examples. But that doesn't mean it's critical in any sense. It just means it works.
Yeah, just as an estimation for this, the free energy barrier you need to.
One over here.
So I would like to make just one comment. So about the mathematical analysis of boundary vortices. So these are the things that so analytically are very well understood in micromagnetics. So even if you have some different shapes, you can also compute the renormalized energies between the vortices. So like this, you can also go to the dynamics. Yeah, so these are works that are, from analytical point of view, are very well understood. So.
One last question then from Epifanio.
Could you just illuminate a little bit more the coupling with the electric field and how you have described it?
Okay, we've only looked at dielectric effects, so there's no effects of electricity in the model as it stands. That's another thing that ought to be done, in addition to backflow effects. It's the standard term that's in the literature. It's the EQ dot E. It's the dielectric effect.
You solve for it?
No, we do not account for Maxwell's equation. It's a constant.
That was the question.
Good. Okay, so that's thank Paula once again.